Hey, it's Mr. Shrum, and we're picking up where we left off from representing chemical reactions. So we are going to visually show you what's happening in these chemical reactions. So when early chemists performed these chemical reactions, they didn't know what was happening at the atomic level, the very small level. However, they found that substances reacted in set ratios. So, for example, in the reaction of hydrogen and oxygen to make water, chemists observed that the gases reacted in the ratio 2:1. So, for every one molecule of hydrogen, you had two, or for every one oxygen, you had two hydrogen. So if they tried to react 4 liters of hydrogen with 1 liter of oxygen, only 2 liters of hydrogen would react. 2 liters of hydrogen would be left over at the end of the reaction. So in this activity, you have a simulation to model making sandwiches and different chemical substances, answer the following questions, and you can use the periodic table to find the names of elements. So let's check out the sandwiches. Yeah, sandwiches. So we have the reactants, which is bread and cheese. So we have 2 slices of bread and a slice of cheese. Those are the reactants. And then you have the products, which are leftovers. Now let's see if you add another slice of cheese. So it could only react with each other to produce a sandwich. And that extra slice of cheese was leftovers. So you can also do that with the bread. But if you add enough ingredients for every 1 slice of cheese that you add another 2 slices, then it is able to make a sandwich. So for every sandwich, you need 2 slices of bread to every slice of cheese. And you can also add meat if you are not vegetarian or vegan. So that can all create 1 sandwich. So 2 slices of bread, 1 slice of ham, I think that's ham, and cheese. But if you add any one element by itself, you can't make a sandwich until you add 2 slices of bread. Okay. So that hopefully helps you with the visualization of what's happening. So the reactants are meat and cheese and bread, if you used just the bread and cheese one. What are the products? So after the reaction occurs, you get sandwiches. Okay, this is all based off of just cheese sandwiches. To make a cheese sandwich, what ratio of bread slices to cheese slices do you need? You need 2 slices of bread to 1 slice of cheese. Try to make a cheese sandwich with 2 slices of bread and 2 slices of cheese. What happens? There is 1 cheese left over. What do the leftovers represent? All right, for this specific experiment visualization exercise, the leftover represents extra slices of bread or cheese that can't be matched up to make another sandwich. They're kind of lone wolves. They don't have enough members to make a sandwich party. Sad day for the lone slice of cheese. However, there is a second part to that. Let's see. Molecules. You can do the same thing with hydrogen and oxygen. So we have 2 pairs of hydrogen and then 1 pair of oxygen, and those create 2 molecules of H2O, water. And the ratio of hydrogen atoms to oxygen atoms, 2 to 1. 2 hydrogen to 1 oxygen. Try to make only 1 molecule of water in the simulation. Is it possible? No, because they come in pairs here. Let's show you the full example. Why can't you make 1 molecule of water? Well, 1 oxygen atom by itself doesn't exist in this simulation. There are always 2 oxygen atoms in the pairs, so you can't separate those 2. You need multiple. So you can make 2 molecules. You can't make 1, but you can make 2. And the top shows you the example. 2H2 plus O2 equals 2H2O. Without changing the screen from part E, count the hydrogen atoms in the reactants and the products. What's the count? So you have 4 atoms of hydrogen in both the reactants and the products because it's a balanced equation. So you have 4 hydrogen and 2 oxygen on both sides. Why is the number of hydrogen atoms and oxygen atoms in the same the same in both the reactants and products? Atoms don't appear or disappear during the reaction. Instead, they get rearranged. Balanced chemical equations. We can describe a chemical reaction with words. We can also describe a chemical reaction with a chemical reaction equation. So for example, this chemical equation represents the synthesis of carbon dioxide from carbon and oxygen. You have C plus O2 to get CO2. Here, CO2 are the reactants and CO2 is the product. Notice in the equation that there's 1 atom of C and 2 atoms of O in the reactants and in the product. A chemical equation with chemical formulas should be balanced. It should have the same numbers and kinds of atoms on each side of the arrow. In some equations, we need to use coefficients in front of a chemical formula to balance the chemical equation. Here's the balanced chemical equation for the combustion of methane. The reactants are methane and oxygen, and the products are carbon dioxide and water. Notice the coefficient 2 in front of oxygen and the water in the equation. So everything's balanced, okay? And the image shows how to count the atoms in the chemical equation for the combustion of methane to find out whether it's balanced or not. There's 1 atom of carbon, 4 atoms of hydrogen, and 4 atoms of oxygen in the reactants. The product also has the same numbers and kinds of atoms. So this equation is balanced. And there is an activity on the next screen to see step by step how to check whether a chemical equation is truly balanced. You have carbon, oxygen, and hydrogen. Here's 1 methane molecule. You have 4 hydrogen and 1 carbon molecule. And you have 2 oxygen molecules, which come in pairs because of O2. And that reacts, and the products we get are 1 carbon and dioxide molecule. So we have a CO2 with 1 carbon and 2 oxygen. And then you have 2 water molecules. So 2 oxygen and 4 hydrogen atoms. So here we are checking whether the atoms in the chemical equations are balanced. So here's the example here. There are 2 nitrogen atoms and 6 hydrogen atoms. Draw the atoms in the 2 molecules of ammonia. Oh, whoops. So here's what they look like. You have 2 nitrogen and 3, 6. So 2 pairs of 3 hydrogen atoms. So 2 nitrogen and 6 hydrogen atoms. Now compare the numbers of nitrogen atoms and hydrogen atoms in the reactants part B and the products of part D. So you're looking at B. So you have 2 nitrogen and 6 hydrogen. And you also have 2 nitrogen and 6 hydrogen. They are equal. If the numbers and kinds of atoms are equal in both pictures, the chemical equation is balanced. If they're not equal, you still have some work to do. Is the chemical equation balanced? Yes, it's balanced because the atoms match up to both sides of the equation. Now we have another chemical equation, nitrogen plus hydrogen. This time we're going to use different methods to count the atoms. Multiply the coefficient by the subscript for each atom. For example, to find the number of hydrogen atoms in 3H2, multiply the 3 by 2. That gives you 6. Use the following table to organize your work. Fill in the number of atoms in the reactants and products in the table. Here we go. So you're just multiplying the coefficient and the little number known as the subscript. So 3 times 2 equals 6 hydrogen. 1 times 2 equals nitrogen, 2 nitrogen. And then on the other hand, you have 2 times 3 still equals 6. 2 times 1 equals 2. And they are equal. Equal atoms in the reactants and equal atoms in the products. This equation is balanced as well. Cool. All right. And this is just to test if you can use the methods that we just learned. In the reactant side, the left-hand side, there are 4 carbon atoms. And you get that by multiplying 2 times 2. 4 carbon atoms. To get hydrogen, you have 2 times 6. And that is 12 hydrogen atoms. O, you get 7 times 2, 14 oxygen atoms. The number and kinds of atoms on both sides of the chemical equation are the same. So that means the chemical equation is balanced. This equation shows that the neutralization of sodium hydroxide and hydrochloric acid. The reactant side of the chemical equation has 1 atoms each of sodium, hydrogen, oxygen, and chlorine. Oh, sorry, no, it has 2 hydrogen actually. So only 1 sodium, 1 oxygen, and then 1 chlorine. The reactant side also has 2 hydrogen atoms. And then count the numbers and kinds of atoms on the product side of the equation. The numbers and kinds of atoms on both sides of the chemical equation are the same, so that means it's balanced. So just to double check, you have 2 H's over here, you have 2 H's over here, 1 O over here, 1 O over here, 1 sodium, 1 chlorine, 1 chlorine atom. So you're good to go. Now we're going to talk about the law of conservation of mass. Early chemists found that the mass of a system at the beginning of an experiment was the same at the end of the experiment. This discovery led to the conclusion that during an experiment, no new matter is created and no new matter is destroyed. This principle is often referred to as the law of conservation of mass. A balanced chemical equation reflects this law of conservation of mass. All right, so a scientist conducts a chemical reaction, and at the beginning of this reaction, she combines 5.4 grams of the first reactant and 6.3 grams of the second reactant. She runs the reaction in a closed chamber and heats only the reaction. A small amount of gas is produced. What can you conclude about the total mass of the substance present when the reaction is complete? The mass equals 11.7. And where did you get that number? You have 5.4 plus 6.3. That gives you 11.7 at the beginning of the reaction. And there is a conservation of mass. So at the end, the mass is the same, 11.7 grams. No adding or subtracting. Now we're going to look at careers in science. Nanotechnology is a new type of chemistry, relatively new. People create tiny structures made of atoms. How tiny? Well, consider that a sheet of newspaper is 100,000 nanometers thick. So that should give you some scale, some idea of the tiny structures they're dealing with. So in nanotechnology, people manipulate atoms at a very small scale. The tiny structures that are made can't be seen by the naked eye. There are many different kinds of nanostructures. One kind of structure is a very small tube, which is called a nanotube. And this right here is a carbon nanotube. Each corner of a hexagon is a carbon atom. So that's really small. And scientists make these structures in labs called clean rooms. And these special labs prevent contamination from people's bodies or clothes. So that's why they're wearing those safety clothing. This precaution is necessary because the structures are very small. Even a speck of dust might change the product. Scientists use nanotechnology to make many products, and here are a few. Ultra black coating that absorbs all light, miniature fibers that lengthen and shrink to build very small artificial muscles for tiny robots, nanotube sponges that soak up oil spills, nanotube containers that deliver drugs directly to cells in the human body. And here's some more pictures. So if you want to work in this type of industry with nanotechnology, technicians operate specialized equipment and produce, test, and modify nanomaterials. Engineers, of course, in the field of nanotechnology, develop and test new products that use nanostructures. Research scientists make new kinds of nanostructures. Read more about nanotechnology as a science and a career. If you click on that link, here, I'll open a new tab. Nano.gov, the National Nanotechnology Initiative, and it just gives you a short little explanation and other resources up here. And that brings us to the summary. And that's it for atoms in chemical reactions. So way to go. Oh. So thank you for sticking through this lesson. Hopefully you learned a bit about the conservation of mass and how atoms on the left-hand side of a chemical equation should be balanced by the right side. Because atoms are conserved, no mass is created or destroyed. And that gives us balanced chemical equations. And that should help you understand the ratios of atoms to other elements in these equations. So if you have any questions, please email me or message me in Canvas and I can help you out. But until next time, see you all later. Bye-bye.